the undergraduate, all of you must have taken some course in thermodynamics, I'm assuming. So this course will be more or less along will have similar content, right? So I will hand out the list of topics that we would cover, along with a list of references for this course, and how the grading will be done. Maybe tomorrow again, because I want to assess how many students are there before I make a copy of the syllabus and so on. Right? So I'll hand that over by the end of this week. Right? And but I'll briefly explain what this course will cover. First of all, the title is somewhat misleading because this course is neither advanced nor will deal with thermodynamics actually. So thermodynamics means something which is changing with time in mechanics. When you have when you're studying mechanics, you have studied statics on the one hand as well as dynamics. Statics is when the body is at rest, and then you look at what are all the forces that are contributing to this state of rest. Dynamics refers to a body in motion, and then you try to understand how the body is moving as a function of time, right? So dynamics refers to something in motion, whereas in this course we talk only about thermostatics, or often referred to as thermodynamic equilibrium. So we look at properties of systems, right, which are at rest or at equilibrium, that means they are not changing with time at all. We look at only those systems. So this is really not a course about thermodynamics, but rather about thermostatics. Right? But as an introduction to that, the topic of thermostatics, or sometimes referred to as thermodynamic equilibrium. The important point here is that the thermo, that is there is an exchange of heat. Thermodynamics was originally coined to refer to a heat engine as a thermodynamic engine, right? So the effect of heat, how it acts on an engine and how it makes it move, the interrelation between heat and motion. That is how the name thermodynamics came into existence. But even the classical thermodynamics started out with the objective of how bodies move under the action of heat. However, for the purpose of this course, we will deal only with bodies which are in equilibrium. That means the properties are not changing with time, and yet the properties are of interest to us. Right? So that is the part of thermodynamics that we will take up. Right? So as an introduction to thermostatics, it is still important to understand at least the classical thermodynamics, what it discovered and what thermostatics made use of from the classical thermodynamics. Right? Because many of the equations that we will use in this course in thermostatics will look very similar to the equations that were discovered in what we may call as the classical thermodynamics, which roughly covers periods 1820 to 1854, right? And it's important to understand that portion of thermodynamics because that will be an introduction to thermostatics, and we will see how that is the case, how something that began as a study of bodies in motion actually came to be used to study properties of a system in equilibrium. That introduction I will give maybe within 1 or 2 classes, and then we will move on to the main portion. Are there any questions before we begin? Any questions? No questions? Okay, then I'll continue with the introduction. So, what we will deal with is what we may call as a classical thermodynamics. Classical thermodynamics, and attention was focused on a very special class of systems. So thermodynamics is basically a relation between heat and work. We broadly classify that as the objective of thermodynamics. When you heat a body, what happens to it, or what can happen to it, and how to predict what can happen to it. So basic objective of thermodynamics, and in fact Carnot himself said that this was his objective, to look at what will happen to a body under any circumstances. His objective was very general, to create a very general class of motions and systems. But yet he himself restricted his attention to a very special class of systems. Now we'll list the properties of this special class of systems. The special class of systems basically is the bodies are homogeneous in nature. Homogeneity is a certain uniformity, right, in the properties of the body. So we know that when we add, for instance, heat to a system, right, when we heat a body, a fluid, right, two things can happen. One, its temperature can change, right, and its density can also change. It can expand or contract. But what was assumed in classical thermodynamics, when for instance you add heat to a body, its temperature, let's say, can increase, but this increase will be the same at all points in the body. So the temperature increases at one point, let's say from 10 degrees to 15 degrees. It will do so at all points simultaneously. So that is what we mean by homogeneous or uniform systems. So I need to specify only one temperature. We all know that, for example, heat conduction is already known at that time. When you heat a solid, for instance, temperature, there can be gradients within the body. So if I have a piece of metal and I have heated it, and I know that its temperature is varying, can be a function of position or location within the bar, solid bar, let's say. Right? Then I have to specify the temperature of the body at each and every point in the body to know the temperature profile. For instance, let's say you have a solid slab that is being heated, and then its temperature I know can be, let's assume, one-dimensional heat conduction, right? So let's say this is T1 and T2, right? The body is heated, and I am saying that the temperature is not uniform. This is the phenomenon of heat conduction. Temperature is not uniform, but it varies from point to point. Then, if I let's say I have a slab of length L, so I have to specify the temperature at each and every point. And in fact, if it can be three-dimensional, I have to specify it everywhere within the body. Right? So that means I have to specify an infinite number of temperature values to precisely represent the state of the body with respect to temperature. But when I say that all points within the body will have the same temperature, then I need only one temperature, one value of temperature to specify the state of the body with respect to temperature. The state of the body was recognized, that is the thermal variable. The mechanical variable, if I consider a body of fixed mass, then I say there are no density gradients within the body. So then what it means is that the density of the body is also uniform. So if I am going to fix the mass, then I can specify the state of the body, the thermodynamic state of the body, by specifying its temperature as well as specifying its volume at a particular instant of time. So this can of course change with time. That is when we study thermodynamics, something is changing with time, right? But at every instant of time, I need only two variables: the temperature of the body as a whole, the volume occupied by the body of fluid. So specifying the density, I specify the volume. That is a conventional way of specifying. Right? So you know in fluid mechanics, for instance, when a fluid is variation of the density with position, or might have also seen versions of the continuity equation where the density actually depends on the position. In thermodynamics, right, it was assumed that the density remains the same. So I might specify the density because I'm fixing the mass, considering a closed system. I specify the temperature and volume. The body as a whole, but it will vary as a function of time. So when I see a body has undergone a process, right, then I will say that, let's say, starting from time t to some time, let's say t bar, I need to specify the temperature and the volume. So when I need to specify these two variables as a function of time, I have specified the full details of the process undergone by the body, or you can give it as a plot. It might change like this, and volume might change like this over a period of time, let's say. Another important variable is the pressure experienced by the body of fluid. The pressure was assumed to be given by an equation of state. So you need not actually have to measure the pressure separately. So assume that every body has an equation of state. The equation of state relates the pressure of the body to its volume and temperature. Right? So since we are assuming the temperature is the same at every point in the body, so I can talk about the pressure of the body as a whole. So everything is uniform. The pressure is also the same at all points within the body. It is determined by specifying the volume of a fixed mass of fluid and its temperature. So the pressure in effect is also a function of time, because the volume and temperature are also functions of time. So if I know the equation of state, then by giving from this, I can also specify the pressure. These are the basic variables of interest in thermodynamics: volume, temperature, and the pressure. There's an equation of state that relates the three variables. What about the heat and work? Right? We need models for those. So the heat and work, they will denote a bit differently from what is normally done by specifying the rate of at which work is done by the body and then the rate at which heat is added. Rate, this is a rate to the body. The rate at which work is done, the rate at which heat is added to the body. The work that you know the sign conventions, work done by the body, on the body, similarly heat added to the body and heat removed from the body. So to avoid the confusion, we adopted a very standard sign convention. So I refer to WR, the rate at which work is done by the body. WR is positive, then net work is done by the body at that instant. Right? Similarly, heat added to the body we regard as positive. So if QR turns out to be negative, then that means heat is removed from the body. This is a sign convention that we adopt. Now, classical thermodynamics adopted some specific models for the work and heat, right? So what are the specific models? WR is given by V dV by dt. The rate at which work is done by the body, right, is given by the pressure times the rate at which volume is changing. Now, generally, if you are given the rate of heat and the rate at which heat is added and the rate at which work is done, what can we say about the total work done by the body? Let's say the process takes place between time t1 and t2, right? So what can you say about the total work done by the body? So it will be an integral of the rate at which work is done by the body. So we may regard the work done by the body during the process, I need to specify the rate at which work is done by the body at every instant, then I just integrate. For instance, here, when given d of t, then I can easily calculate dv by dt, either numerically or whatever, right? And then I can calculate the pressure, is also calculated from the equation. So I can easily calculate what the work rate at which work is done at every instant. It's an instantaneous rate, right? If I want to get the net work done by the body over the whole process, which let's say takes place between t1 and t2, if we want to use a consistent notation, I can start with some time t1 and the process ends at some time t2. It's totally arbitrary. That's our focus of attention on what happens to the body. So then this model is independent of these concepts. Concepts are general, that we assume that there is a rate at which work is done by the body. The net work done by the body is given by the time interval of that. The same way we can specify the rate at which heat is added to the body, and the net heat added to the body over the process is given by the time interval of the rate at which heat is added to the body at every instant. These are general concepts, but classical thermodynamics use particular models for WR and QR. It's very important to understand what those are. These are very specific models, but they are not universal models. Concept of rate of work done and rate of heat added are very general. The particular models used in classical thermodynamics are very, very special, as we will see. So this is what it is. So now what can we say about the work that is added or work done by the body is simply P dV by dt times dt. What can you write it as? Is equal to what? Yeah, volume dV by dt is the derivative of the volume as a function of time, because volume is a function of time. The derivative is well defined. So now V also can be found as a function of time. V is a function of time. This whole interval is a time interval. That's fundamentally the work. Because when you talk about work done in a process, when I mean a process, it means things are changing with time. The trivial process is when neither its volume nor temperature is changing. That is a body at rest and nothing is happening to it. That's not of interest in thermodynamics. There is no work done by the body, there is no heat added to the body, net. Right? But we are interested only where some changes are happening. But what can I write this equivalently as? How do you normally calculate the work in any thermodynamics course? Integral PdV. So I can write this integral PdV. But now an integral over time becomes an integral over volume. How can that happen? Right? This integral you can all understand is very easy to evaluate. You know the volume and temperature process is given. Volume and temperature are functions of time. So what is the first term? Pressure is a function of time. I know how to calculate. Volume is known as a function of time. Temperature is known as a function of time. Pressure I can calculate from the equation of state as a function of time. Right? And then the rate of change of volume can also be determined, because I know how the volume changes with time. I can calculate the rate at which volume is changing, is increasing or decreasing. It could be increasing over part of the process, it could be decreasing over the rest of the process. We don't know. We are not concerned about particular process. So this integral is very easy. I have a function of time which is integrated with respect to time from some time t1 to t2. That integral everybody knows how to evaluate. Right? Now what about this integral? PdV. What is now the pressure a function of? In that integral, the second integral that I've got, integral P dV, what should be pressure a function of? Volume and only volume and temperature also, right? That's correct. But how would we evaluate this integral? But we all know how to evaluate an integral like this. Very easy. Now this integral is like this. Now I have another integral. Now I have another integral. Does the integral have any meaning at all? Because I cannot put just x equal to a to b, because this is now a function of both x and y. Clearly this integral is like this. It's an integral over volume, but the integrand is a function not only of volume but also of another variable, the temperature. So how would you evaluate this? Does the integral have any meaning at all? Or when can it have a meaning? When can it have a meaning? That's fine, that's what you're all doing. In actual thermodynamics course, you're dealing with isothermal process. So it becomes very easy. You cannot make the temperature constant when it is not. If you are talking about an isothermal process, what you are saying is correct. That's a good answer. Suppose I am talking about a process where the temperature is not changing, right? But the volume is changing. It could be. That could be isothermal process. Your temperature is fixed, let's say at T0, but volume is changing. Then it becomes very easy to evaluate. All I have to do is specify what is the volume at time T1, what is the volume at time T2. I can evaluate the integral. But that is not a general process. In a general process, both temperature and volume can change. So if I want to evaluate this integral, what should I do? Exactly. So we need to specify the relationship between the temperature and volume. We know the relation because T is a function of time. T is also a function of, volume is also a function of time. The temperature and volume are related. For that, we need to associate with the process what is called as a path connected with the process. That path will be not on the time domain but on the volume temperature domain. So what I can look at is, given a general process, right? Given a general process, now I can map it onto the volume temperature quadrant. Well, I say quadrant because volume and temperature we're talking about absolute temperature, so they have to be positive. So I can focus my attention on T and V. Now if I want to project the process onto the TV plane, how would you do it?
So there has to be one common variable between them.
There is no one. The common variable is the time. Now I want this process. Let's assume I have this. I've given this T versus T, V versus T. Now if I want to project it, what would I do? How would you do it? Actually, practically. It's quite easy, right? So I take a particular time, T1 let's say. So I know T1, capital T1, V1. So what do I do now? Take V1, T1, the volumes and the temperature, and simply mark it on this, right? So let's say I have V1, then I take the next point and so on, and then I connect it and I get to the T that always be increasing volume and temperature. Just take it as an example, right? So some values are given, it could go up and down also, right? So this is what I mean by the path associated with the process, right? And what is called as summon point. And now certainly I can define this by an equation, right? Because y is a function of x, so clearly t is a function of volume. So all I need to do is put that here, it's actually here, and then I can carry out this. Actually, this is what is called as a path integral or a line integral. So the very specific model for the work done by the body used in classical thermodynamics means that I don't really have to know the full details of the process, right? All I need to know is the path associated with the process, and then I can calculate the work by simply evaluating the path integral without knowing anything about the process other than what path it maps onto. So it's certainly possible to give examples where two different processes, right? Two different processes map onto the same path. So what it means is that the work done in those two processes would be the same. I can give a very simple example, a trivial example. Let's take the process where the temperature is constant. Isothermal process. It's an example, right? So T equal to T naught, right? And I'll take the process 1, T equal to T naught plus alpha times T. Alpha is some constant. It's linearly increasing, let's say. Right? Now I'll consider this process between a time 0 and T bar. B is at time T equal to 0 is V naught. After that becomes V naught plus alpha times T bar. Now I consider a second process. Again T equal to T naught. V equal to V naught plus 2 alpha T. And now here I consider the process only between a time 0 and T bar by 2. Do you agree that these two processes are actually different or not? Or are they the same? Processes are same or different? Different, right? So we can focus only on the volume. That's why I suppress the temperature, a change, constant temperature. This is volume is increasing at a rate of alpha. Here the volume is increasing, let's say alpha is greater than 0. Do it's twice as fast as this. But of course I am considering this process only over a time T bar by 2. Now what will be the path corresponding to process 1? You start, the temperature is fixed. So it is going to vary on this. Volume V naught, right? At the end, it is V naught plus alpha times T bar. So this is the path that will be noted by descriptive P. Now what about the path for the process 2? Right? So it will again start with V naught. It will end again with V naught plus alpha T bar. It has to remain at the same temperature. So the path associated with the second process is the same. I've just given a somewhat trivial example where two processes taking place at two different rates, one twice as fast as the other, right? But both of them having the same path on the volume temperature quadrant. So what can you say about the work done in process 1 as opposed to, so we know that P1 is not equal to P2. The processes are different. What can you say about the work? Work then is the same, because if you adopt this model, only if you adopt, this is not true in general. You don't expect the work done by a body to be the same in two different processes, especially one twice as fast as another. Because we assume that the work, rate at which work is done, is given by PdV by dt, or the famous PdV or PV work. We've assumed that that particular model makes the work done dependent only on the path traced out by the process. So two processes are different, they could have the same work done provided they map onto the same path. So the work becomes path dependent, and so that is why the work done will be the same. Now, this is also closely related to the notion of reversibility, in which it was used in classical thermodynamics. Because we know that, for instance, if I have an integral a to b f of x dx, right, we know that it's equal to minus integral b to a f of x dx. It's a very well known result in single variable calculus, integration. Now, path also has a direction, because I could go from here to here, and so I have to denote there's a direction associated with it. So when I say P, there's a direction. Now I could think of the whole process being carried out in exactly the reverse sequence, so that I start from P2 T2 and trace the same events sequentially, and so that the path now becomes from V2 T2 to V1 T1. So that is the reverse of the process, and the path then would have to be denoted as negative of P. The same process effectively, but it's carried out in the reverse direction. All the volumes and temperature occupied or taken or assumed by the body are there in both the processes, but I think in the reverse direction effectively, right? So when I now look at the path, I also have to take that into account, and there is a perfect analog of this result, that if you calculate the same, suppose let's say I have P bar of Vt dV along one path, and then I take the reverse of the path, that is I carry out, consider the path in the opposite direction, then you can very easily show the standard result. We are not going to be interested in proofs of these results, but it's a direct extension of this idea, which you all know in a to b is minus integral b to a, the same function. The same way, integral, that's a path integral, right? Along a particular path, the value of the integral will be the negative of the value along the reverse of the path. So the reverse of a process, let's now focus on P1, right? Any process, not just an isothermal process. So if we consider the reverse of the process, then it will be mapped onto the reverse of the path, right? So from that, I get the important relation that the work done in a particular process is simply the negative of the work done in the reverse of the process. So the whole process is carried out in the reverse direction, right? Then the work interaction, a certain amount of work is done by the body, then the same magnitude will remain, but now the work has to be done on the body. So the magnitude of the work remains the same, but the sign changes. So it is in this sense that a process may be called reversible, in that you could reverse the process and the work interaction in magnitude will remain the same, but change in terms of sign, right? So that is the idea in which reversibility was used in early thermodynamics. Now gives a concrete definition of reversible. Now adopting this model means that all processes are reversible with respect to work done. There is no question of considering any irreversible process in classical thermodynamics. Now we have said that thermodynamics is a relationship between heat and work. So this is the model that was used for work. You are now very familiar. It's the famous PdV work that you all know about, but only written in terms of the rate here, so that you can see how the reversibility comes into play. Right? This model is changed, then we could consider the irreversible process, but as long as you are focused on this particular model, we make all processes reversible. What is the analog this model used for the rate at which heat is added to the body? Right? That I will now discuss. And we also have a similar form to the rate at which work is done. Are there any questions at this point? understand the notion of a process is very well known. We are now restricting on homogeneous bodies, so volume and temperature. Just focus on that. Process means I have to give the volume and temperature as a function of time. So with every process, whether it's reversible or not, is associated with a path. Right? How do I construct the path? Just take each value of volume and the corresponding value of temperature and simply plot it on the volume temperature axis. That's the path. Right? Now, why is the path important in classical thermodynamics? Because the particular model used for the work done will make the work dependent on the path alone, in the sense that two processes which could be quite different but mapping onto the same path, right, we have the same amount of work done. Right? And then you consider the reverse of the process, the path corresponding to that would be the reverse of the path of the original process, the work interaction, because the work is determined purely by the line integral, right, independent of the time integral. So there is a relation. A particular process will give rise to a particular path. As we have seen, two different processes can give rise to the same path. That is why we say that the work becomes path dependent. So as long as you specify the path, I don't ask for any details about the process. I can calculate the work done, right, in classical terms. That's not true in general. In general, we need to give the full detail of the process. Yes?
So, shouldn't we represent the plane as T versus B, because the work is integration of P dV, and it may so happen that the T versus B graph is not actually corresponding to the P versus B graph.
No, T versus B is not. T versus B is, you have to calculate T versus, from the T versus B, you have to calculate T versus B.
So because it can happen that from the T versus B graph, we can feel that the path is the same, but from the T versus B graph.
No. T versus B doesn't have anything to do with the path. The T versus B gives the path. So that will help me construct the function P as a function of volume alone, and then I go and integrate it. Right? With the P versus V, it is very simple. It is like this. I want to reduce that. Finally, it reduces to that. When I specify T as a function of P, then the integral can be written as V1 to V2 as some function of V alone. And then I can calculate it like this. So P versus V has nothing to do with the path. That comes only the path. By path, the volume and temperature are the basic variables in classical thermodynamics. The process is specified by specifying them as a function of time. Path is mapped onto the volume temperature quadrant. P doesn't come into the picture. There's no path connected with the pressure here. Yeah, work for the work, then I have to find P as a function of volume. Right? So for that, the path will be helpful. We don't talk about the reverse of the path on the PV. That also might turn out to be. If you're taking the reverse, then the integral would be simply the negative. It might be V2 to V1 of the same function. It will happen like that.
Actually, we can determine the work done is same for two processes from the T versus B graph. We cannot determine.
We cannot determine generally, but as long as the work done is given by this model, we can determine. That's the fundamental theorem of calculus, which says this equality I have written and is conveniently sort of proved by simply cancelling the dt and dt here. But that's not the way it works, because here I have pressure as a function of temperature. This is actually a derivative, it's not dV of T. You can't just cancel, but there's a fundamental theorem of calculus which says that this integral is P times dV by dt integrated over time is equal to P dV. That is why the idea that it is a path integral is not very clear by just cancelling dt and dt. So here, actually, I have to say that the path, that is why the path becomes important. Right? So now look at the analogous model for the heat added. It's somewhat straightforward if you recognize that the work is purely a mechanical quantity here, right? But when you add or remove heat, not only its volume can change, but its temperature can also vary. right? So any model for the rate at which heat is added would have to take that into account. It should have a term concerning the volume change. There should also be a term connected with the temperature change. So that is the model that was adopted. The model is a somewhat an extension of that, and that is given by this model. So we have both dV by dt, because when you add or remove heat to a body, its volume can change. So this coefficient lambda b determines how it will affect the volume change. Then there is another quantity which has to be introduced, because when you add heat, its temperature can also change, right? So we need both coefficients, but effectively it is the same in that the rate at which work is done is proportional to the time rate of change of volume, right? So it is not proportional to time rate of change, it is proportional to the, let's say, the time rate of change of volume squared, let's say. Then this whole argument will break down. So in the same way, the heat was also regarded as proportional to the time rate of change of volume plus a term which is proportional to the time rate of change of temperature. So that being heat, it has to account for both volume and temperature changes, right? Basically, its dependence on dV by dt and dT by dt would make the heat, for the heat also, the same arguments would follow. So if I want to calculate Q, then it will be QR dt, be lambda v dV by dt plus Cv dt by dt times dt. And then by a theorem of calculus, it can be easily shown to be this. It's now slightly more difficult integral, but effectively it is the same. For instance, if I want to evaluate this, right, I would equate d as a function of volume, then I know it's just like p dv. Now for this, since this is an integral over t, I may express v as a function of time, temperature, and calculate that part of the integral, right? Typically what is done is you use a parameter to parameterize both volume and temperature, and then you can evaluate the integral in terms of the parameter as a single value integral. But we are not interested in that. But basically, what this would also mean is that Q of the process is simply the negative of the Q of the reverse of the process. The reverse of the process will trace the reverse of the path. This is very much a line integral, just like this, right? And so both the heat and work interactions are reversible in that sense. So the body undergoes the reverse of the process, right? Then it will be mapped onto the reverse of the path. The heat interaction in the backward, the reverse process will simply be the negative of the heat interaction in the forward process. That would make both work and heat interactions reversible. In that sense only, it was regarded as reversible. And hence, all processes in terms of work and heat interaction both are to be regarded as reversible. Nothing else is allowed as long as I speak. Now this quantity is very important. It was called as the latent heat with respect to volume. It has a similar connotation to the latent heat which we associate with the phase change. But there also temperature is not changing. That's why this is the specific heat or the heat capacity at constant volume that you are all familiar with. Right? Heat capacity at constant volume. This is somewhat new because it's hardly ever discussed in any of the modern textbooks on thermodynamics. It's a very important quantity in classical thermodynamics. We will see its importance in tomorrow's lecture. Are there any questions? I will mention that for this part, this portion today and tomorrow, that will not be covered in the quizzes, it's only for motivation. I can give you some references for that, but you simply have to keep the broad outline in mind. That will not be a part of the main course, right? So because there are not very easily available textbooks available, readily usable textbooks. So I'll summarize this by the end of tomorrow's class, and then we'll go on to the main portion of the course, which is thermostatics, as I said. So I'm done. You can leave. Attendance will be taken. See.